Hello everyone, welcome back to the MOOCs course on Advanced Analytical Technique. Today I am going to finish the second unit of this course, Molecular Luminescence Spectroscopy. It is the fifth lecture of the sixth week, and the lectures that you have attended so far has completed two important topics. First is the absorption and emission spectroscopy, in which we have discussed about atomic absorption and atomic emission spectroscopy and how the techniques are and how the analysis is being done, what are the components, what are the detectors, and how important those techniques are. And then we have started the second unit, the molecular luminescence spectroscopy, in which we have studied two different phenomena, the photoluminescence and the chemiluminescence. In photoluminescence, we have learned about fluorescence as well as phosphorescence. After completing the instrumentation, the principle and related topic to the fluorescence and phosphorescence, in the previous after completing few related topics of fluorescence and phosphorescence, including their instrumentation, working principle, etc., I have discussed with you the chemiluminescence and how measurements are being done using spectrophlorometer. Now in today's lecture, I am going to discuss some examples with you, how we analyze a spectra, how we do some numerical problems based on the data we obtain from fluorescence spectra. Let us start with today's discussion. As in all spectroscopic techniques, we first of all prepare a calibration curve which is needed for the quantitative analysis. I hope you remember that in case of atomic emission and atomic absorption spectroscopy as well, I told you the importance of calibration. I told you about the calibration curve, what is it and what is the importance of a calibration curve, and I told you there that how a calibration curve is prepared. Again, for your just a recall, calibration curve is basically based on some known concentrations. For these known concentrations, we perform the spectrum. For these known concentrations, we perform the study, generate the spectrum, and for these known concentrations, we perform the experiment, obtain the spectra, and from the spectra, we obtain some useful parameters. For example, we determine the intensity of the fluorescence emission, and which is in the form of a electrical signal, because we use photodetector, a photomultiplier tube, or a SSD, solid state array device in this case as well. So what we get at the end is the light intensity is converted into a electrical signal. That electrical signal gives the intensity of the emitted light. So that signal, that the value of that signal is taken, and then a graph is plotted between those concentrations, the known concentrations. Generally we sometimes we go for concentrations in ppm. For example, sometimes we go for concentrations in ppm, like we have 10, 20, 30, and so far we prepare 5 to 6 solutions in ppm. However, with techniques like AES specifically, or with fluorescence spectroscopy, since they are very sensitive, so 10 ppm or 20, 50 ppm, it's quite a high concentration for these samples. And as you all know that with concentrated sample, we have some sort of interferences, so the results may not be reliable, and in order to minimize those interferences, we always go for a dilute solution. So instead of taking 10 ppm, 20, 30 ppm for these sensitive instruments, we take 10, 20, 30, and so on, but in ppb level. We take concentrations for calibration curve in parts per billion level, and 1 ppb is equal to 1 microgram per liter, 1 ppb, while ppm is 1000 times more concentrated. 1 ppm is equal to 1 mg per liter. So for making these standard solution, we take a stock solution. For example, in this particular case, I am focusing on riboflavin, which is the vitamin B2. So for analyzing this vitamin riboflavin in a given sample, for example, milk contains a significant amount of this riboflavin. It is used for energy production, it is used for skin health, and it is very useful for the body. So if we are going to check the amount of riboflavin B2 in the milk that is given to us as a sample. First of all, we take a pure standard solution of riboflavin, which is called as a stock solution because its concentration is high. Its concentration is 100 ppm. Now we first of all take this solution from the refrigerator, keep it at room temperature, and allow it to just comes to the room temperature, or allow it to equilibrate to the room temperature, so that volumetric measurements can be done consistently, because at low temperature the volume may have some difference, while if we compare it with the volume at, for example, in case of water as well, at 4 degree the volume is a little bit higher. So we allow the solution of this riboflavin to equilibrate to the room temperature, and then we take 1 ml of this solution and dilute it to 10 ml. For example, we have a standard flask, and in this standard flask we have this 100 ppm solution, which is called as stock solution. Now this stock of 100 ppm of B2, from this we take 1 ml in a small standard flask, and then we add 9 ml deionized water or double distilled water. The volume of this flask is 10 ml, so this way we dilute it to this way we dilute it 10 times. So earlier it was 100 ppm, now it becomes 10 ppm. So in this way a diluted solution is prepared. The solution of 10 ppm that we have just prepared, we again dilute it to 100 times. We again dilute it 100 times by taking 1 ml of this solution, and adding 99 ml distilled water or deionized water. Then it becomes 100 times dilution. Its concentration will go 10 upon 100 ppm will be equal to 0.1 ppm. Now this 0.1 ppm can also be written as 100 ppb. Now this is our main solution. From this solution we will prepare 5 different solutions, and those solutions are numbered as 1, 2, 3, 4, 5, and those solutions are numbered as 10, 20, 30, 40, 50 ppm, 50 ppb, and one more solution 0 ppb, which does not contain the sample, which contains deionized water only. Now these solutions are prepared in 10 ml standard flask. Now these solutions are prepared in 10 ml standard flask. In this way. And in these 10 ml standard flasks, in the first flask we put 10 ml distilled water only, while in the second we put 1 ml of this solution, 9 ml distilled water. Here we put 2 ml of this solution, 8 ml distilled water. Then we put 3 plus 7 ml distilled water, then 4 ml of this solution, and 10 ml distilled water, and 6 ml distilled water. While in the last one we put 5 ml of the above solution, while in the last one we put 5 ml of the above solution plus 5 ml distilled water. We just make 2 times diluted, so the concentration comes from 100 ppb. It is when it is diluted twice only, it comes to 50 ppb. So we have 5 different solutions, and now we'll do the fluorescent measurements by using a spectrophlorometer. It will come out to be like this. Here we have intensity of the light radiation, which is in the form of millivolts because it's an electrical signal. Here we put these solutions. We have 0 here. So then we'll plot this data for calibration curve preparation. This is intensity in millivolts. Then we have 0, 10, 20, 30, 40 and 50B. ppb. The corresponding the corresponding signals will be measured from the fluorescent measurements using spectropolarimeters. Those field signals are plotted here, and finally a straight line is observed. Some of the points lie exactly on this straight line, while some of the point falls little bit outside the line, but still we get a straight line showing a linear relationship between the concentration of riboflavin or B2 with intensity. It is linear. Now our calibration curve is ready. The next step is to take the sample of the milk, remove some interfering agents like fats, do some filtration, and then the sample is ready for analysis. We put the sample again in the cuvette for measurement of fluorescence spectra. We put the sample again in the cuvette for measurement of fluorescence, for measurement of fluorescence spectrum, and from there we obtain the electrical signal again. Now the electrical signal that is obtained falls on this particular line. Say for example the signal falls somewhere here. Now we draw a perpendicular to the y-axis because the signal falls here, and now then we draw a perpendicular to the x-axis and the point, sorry, so now we draw a perpendicular to the x-axis just to know the point at which it cuts the x-axis, and the point at which this perpendicular cuts the x-axis is the concentration of analyte in the sample. This gives us the concentration of riboflavin or vitamin B2 in milk. For example, it is cutting at somewhere around 36 ppm, so 36 ppb. This means that our milk sample contains 36 ppb of riboflavin. This is just for an example. So this is again preparation of unknown solution, means this is our sample. So in this particular case, we have, as I told you, we have to identify the concentration or the quantity of B2, vitamin B2 or riboflavin in milk. So it is a dry milk sample. We take this dry milk, reconstitute again in water, and then we remove interfering fats and proteins so that they should not interfere with the data. They should not interfere with the light that is being used as a source of excitation, and to have a reproducible and reliable results. Once these interfering fats and proteins are removed, a small procedure is carried out on the milk sample. We take 10 ml of the milk sample, add exactly 75 ml of the solution consisting of equal parts of, this is acetic acid and NaCl. So we prepare a solution with 3 molar acetic acid, CH3COH. They are added as agents to support the process of excitation, and then we have 3 molar NaCl. They just added in the solution. This is part of procedure, sometimes just to remove interfering agents, sometimes do some they just support the excitation as well. So this solution is prepared, and then 75% of ml of this solution is added, and then 75 ml of this solution is added, while 25 ml of the milk sample. So milk sample is diluted 4 times. From 25 ml we are making it 25 plus 75, the total volume becomes 100. So we are taking from 25 to 100 ml, so we are making 4 times dilution of this sample. Again we do this in a 250 ml or 400 ml beaker to dilute. We do it in a 250 ml or 400 ml beaker for dilution of the sample. Then we stir the solution. Again we filter it just to avoid any suspended impurities or any particle of the fat or the protein. We use Buckner funnel for this purpose. I hope you all have seen a Buckner funnel which is like this and which has small holes inside it. And this funnel we attach to a flask. We pour the sample here. The advantage of using a Buckner funnel is that it has a provision for creating vacuum by running tap water. So we create vacuum by running tap water. We pass tap water which removes all the air, and a vacuum is created, and that vacuum pulls the solvent, and that vacuum pulls the liquid through it, and that vacuum pulls the liquid through these pores, resulting into a fast filtration process. The difference between a normal funnel and a Buckner funnel is that a normal funnel operates on the principle of gravity, means it uses gravity through which the liquid particle moves through it downwards, while the solid particles are retained. While in case of Buckner funnel, it uses vacuum, the power of vacuum, to pull the liquid through these pores a little bit quicker, resulting into the filtration done in a short period, of time. So this vacuum is created by running tap water, which removes all the air. So automatically there is a vacuum is created. We connect this rubber pipe. We connect a rubber pipe to this tube. We connect a rubber pipe to this Buckner funnel for passing tap water. So once the filtration is done, this filtrate is taken. Now it is ready for analysis, means it is ready for measuring the fluorescence spectrum. Again we go for dilution. 5 ml of this aliquot is diluted to 100 ml, and for this we add 95 ml distilled water. Means for diluting it to 100 ml, from 5 ml we add 95 ml of distilled water, so that the total volume becomes 100 ml. And then we can say that the dilution is from 5, since we are going from 5 ml to 100 ml, the dilution is 20 times. So we have done 20 times dilution in this case. So we have done 20 times dilution in this case. Now this diluted sample is taken in the cuvette, placed in the and the spectrum is obtained. From there we obtained the intensity reading in the form of an electrical signal in millivolts. We just put that millivolt reading in, and we just put the millivolt reading in the calibration curve that we have prepared, and we can identify from this calibration curve the actual concentration of the riboflavin in our sample. So in this way the analysis will be done. So remember, in all cases for quantitative analysis, whether we are using molecular luminescence spectroscopy, means the fluorescence spectroscopy, or even atomic absorption spectroscopy or atomic emission spectroscopy, in all cases for quantitative analysis we need a calibration curve, and for calibration curve we need pure sample. We prepare different diluted samples from the stock solution of the pure sample, and then we perform the analysis, obtain data, put it on y-axis against concentration on x-axis, so that a linear curve is obtained, which is the calibration curve. And then we take the real sample, dilute it up to the extent, and then we perform the analysis, obtain the reading, put it on the y-axis, and then correspondingly measure the reading on the x-axis to know its concentration or its actual concentration in the sample. In this way the quantitative analysis is being done. Then there are two rules that I would like to tell you before moving on to some problems. First is called as the Kasha rule. Kasha rule states that in case of photochemistry, when an molecule is excited by absorption of light energy, it is excited from ground level to maybe to the first excited state, or sometimes it happens that it may reach to the second excited state. And as you all know that we have different levels, vibrational levels attached to these electronic states. So according to this rule, there will be some vibrational relaxation first, which brings the molecule from higher vibrational level to the lower vibrational levels of the excited states only. And when the electron reaches to the lower vibrational level of this excited state, then only it comes back and emit light radiations. Clear? It will not happen that electron in the higher vibrational level of this S1 excited state from here directly comes to ground state. According to Kasha's rule, this is not possible. What is possible according to this rule is that first the electron will undergo vibrational relaxation, which is a form of non-radiative deactivation process, and comes to the lowest vibrational level of that excited state, and then it comes back to the ground state, emit light in the visible region. This rule also states that even from the second excited state, the electron does not come back directly and by emitting energy. Means if the electron is in the second excited state by absorbing large amount of energy, it first comes to the first excited state by internal conversion, then only it comes back to ground state, causing H nu emissions. So in a nutshell, I can say that Kasha rules says that both internal conversions as well as vibrational relaxations happens in the excited state, so that the electron from higher excited states comes to the first excited state by internal conversion, and electron also changes the higher vibrational levels and comes back to the lower vibrational levels of the excited state through vibrational relaxations. Both these processes, both these deactivations, means the internal conversion for coming from S2 to S1 as well as vibrational relaxation for coming from higher vibrational level of S1 to lower vibration level of S1, both are non-radiative energy loss phenomena. Both are non-radiative deactivation phenomena, means they do not emit light radiation. They emit heat radiation or some sort of kinetic energy is being lost, thereby electrons comes to those lower level. And then finally, so both these deactivation phenomena means the internal conversion, which brings the molecule from S2 to S1, as well as vibrational relaxation, which brings molecule which brings the electron from higher vibrational level to the lower vibrational level of the excited state only. They are non-radiative deactivation phenomena, means they do not release light radiations. They only causes loss of energy in the form of heat or kinetic energy. And when this happens, the remaining amount of energy is then released when electrons comes back finally to the ground state. And this is the reason, because some of the energy is already lost via vibrational relaxation and internal conversion, and therefore the light energy that is being emitted at the end when electron comes from S1 to S0 is always lesser than the amount of light that is being absorbed. Or I should say, the wavelength of the light emitted is always greater than the wavelength of the light absorbed, because this long wavelength has lower energy, and the reason for this lower energy is that some of the energy has already been lost while changing the relaxation, because some of the energy has already been lost during vibrational relaxations as well as internal conversions in the excited state only, and the remaining amount of energy is being released when the electron comes back to the ground state only, and that energy is released, and that remaining amount of energy is released in the form of light radiations. So this is the Kasha's rule. Clear? So it says that the excess energy, vibrational energy, because the electron reaches to the higher vibrational level of the excited state, this energy is lost via vibrational relaxation. And if the electron is in S2 state, it first of all comes to S1, then only it comes to S0 by emitting light radiation. Here it is only either heat or kinetic energy. This is called as this is called as internal conversion. So both these phenomena, vibrational relaxation and internal conversions, occur in the excited state as per the Kasha's rule. Then only the electron comes from first excited state to the ground state with simultaneous release of energy in the visible region, showing the phenomena of fluorescence. Clear? This now there is another rule, Vavilov's rule, which states that the wavelength of light at which the excitation is taking place, means the excitation wavelength, does not influence the wavelength of light at which emission is taking place, because some of the energy has already been lost in the excited state. Clear? It does not, we can never say that since light of very high energy has been absorbed, now the light energy that is being emitted will also be high. No, this is not possible. No, this is not the case, because even if the higher energy radiation is absorbed and molecule gains large energy, causing electrons to go even to S3 level, but from S3 they cannot directly come to S0. No, this is not possible according to Kasha's rule. From S3 it will first go to S2, then to S1, and finally it comes back to S0. So during these transition from S3 to S2, S2 to S1, the molecules lose some energy, and therefore the energy that is being released in the form of light wavelength, in the form of light wavelength, when it comes from S1 to S0, is totally independent upon the energy that is being absorbed. So this is Vavilov's rule. So we have learned two rules: Kasha's rule, that vibrational relaxation as well as internal conversion takes place, and which causes the electron in the excited state to come to the first excited state and the lowest vibrational level of the first excited state, and then electron comes back to ground state emitting light radiations. Second, Vavilov's rule says that the wavelength of light emitted is independent of the wavelength of light that is being used for excitation, because when excitation takes place, electrons go to the higher excited state. The excess energy is already being lost in the excited state only, and the very small amount of energy that is being left, that is being left is emitted, and the small amount of energy that is being left is emitted when electron comes back finally to the ground state. So this wavelength is independent of the excitation wavelength. Now, very famous Stern-Volmer equation. This equation is basically used when we are using quenching methods. As you all know that quenching methods are very useful methods for studying fluorescence, and the beauty of these methods is that even compounds that do not fluoresce naturally, they can be studied by these methods. And we all know that, for example, we have a molecule which is not a quench. For example, we have a molecule which is a fluorescent molecule. It undergoes excitation. That as excited state is shown by steric. Now we add a quencher over here. This quencher forms a complex and molecule comes back to the ground state. Or sometimes what happens, this quencher gets excited while molecules again comes to the ground state. So this happens in some cases, because so this happens in case of quenching studies. Clear? Even if a compound which is not a fluorescent compound, we can study by this method. How? For example, we have a compound A which is not a fluorescent compound. Now we consider this compound as quencher. Suppose we have a compound X which is not showing fluorescence. Now we consider this as a quencher. And we add it to a fluorescent molecule. Now this fluorescent molecule is showing fluorescence, emitting light at some fluorescent intensity. When it combines, it forms a complex with it, thereby causes reduction in intensity. Or it is called as, or it causes reduction in intensity, also known as quenching. So in this way we can identify the presence of this compound as a quencher. If the quenching intensity if the fluorescent intensity is going down, that means a quencher is present. If there is no effect on the fluorescent intensity, that means there is no compound, then that means that there is no non-fluorescent compound present. Now quenching is of two types. One is called as dynamic quenching, other is called as static quenching. In case of static quenching, the quencher forms a complex with the fluorescent molecule in the ground state only, so that it will not undergo excitation resulting into emission of light. While in case of dynamic quenching, the fluorescent molecule undergo excitation, and in the excited state, the quencher goes and forms a complex. So this is the difference. When the quenching stops in the excited state, it is called as dynamic quenching. When quenching occurs at excited state, it is dynamic quenching. When it occurs at ground state, this is static quenching. Now this quenching is related to some parameters. For example, I naught. So this quenching is related to some parameters, and this equation is called as, and this relation, so this quenching is related to some parameters and this relation, so this quenching is related to some parameters, and this relation or this equation is called as the very famous Stern-Volmer equation. According to this equation, for dynamic quenching, I naught upon I is equal to tau naught upon tau, which is equal to 1 plus kq tau naught square bracket q, means then concentration of quencher, and it is also equal to 1 plus ksv. ksv is the Stern-Volmer constant. ksv is the Stern-Volmer constant into q, again in square bracket, means the concentration of quencher. For static quenching, we have a simplified relation, I naught upon I is equal to 1 plus ksvq. ksv is the Stern-Volmer constant. I naught is the intensity of light in absence of quencher. I is the intensity of light in presence of quencher. Tau naught is the lifetime of the excited state in absence of quencher, means for how long the light is being emitted, the molecule, for how long the molecule stays in that excited state in absence of quencher, while tau is the time or the lifetime of the excited state in presence of quencher. Then q in square bracket is the concentration of the quencher, kq is the quenching constant, kq is the quenching constant, and ksv, as I already told you, is the Stern-Volmer constant. Then sometimes we have static as well as dynamic quenching. So in that case, the intensity ratio I naught upon I means intensity in absence of quencher to the intensity in presence of quencher is equal to 1 plus ksvq, means 1 plus Stern-Volmer constant q. It comes from dynamic quenching. Again we have 1 plus ksvq, that comes from static quenching, since both are taking place simultaneously. This causes deviation from the linear relation. So for static quenching, it is ks into q. Ks is called as the static quenching equilibrium constant. Ks is the static equilibrium, Ks is the static quenching equilibrium constant. And for combined static and dynamic quenching, we have I naught upon I means the intensity ratio. I naught is the intensity in absence of quencher, while I is the intensity in presence of quencher, is equal to 1 plus ksvq. That comes from dynamic quenching, while 1 plus ksq, that comes from static quenching. Because both the quenching are taking place, we have to take the combined, and that causes a deviation from linear relation of quenching and fluorescence intensity. So these are the explanations of these terms. I naught is the fluorescence intensity in absence of quencher, and I is the fluorescence intensity in presence of quencher. Tau naught is the fluorescence lifetime without a quencher, means for how long the fluorescence is being, the light is being emitted. Tau is the fluorescence lifetime in presence of quencher. Then we have q is the concentration of quencher, kq is the bimolecular quenching rate constant, molar inverse, second inverse. Then ksv is the Stern-Volmer constant. For dynamic quenching, we have ksv is equal to kq tau, means the equilibrium quenching equilibrium constant, and tau naught, the lifetime of fluorescence or the time duration up to which fluorescence light is emitted. Tau naught into kq, the equilibrium quenching constant, and finally ks is the static quenching equilibrium constant. These are the explanation of these terms. The key concept, as you all know, fluorescence quenching means the reduction in the intensity of the light being emitted during the phenomena of fluorescence, and it happens because of the presence of a quencher. Now dynamic quenching, as I told you, these quenchings are divided into two categories, the static quenching and dynamic quenching. In case of dynamic quenching, the fluorophore or the fluorescent molecule undergo excitation by absorption of energy, and it reaches to the excited state, and in the excited state the quencher comes and form a complex, so that in the excited state only the molecule undergo complexation with the quencher, and then the energy is released in the form of a non-radiative deactivation. Clear? No visible light is emitted. This is called as dynamic quenching. So it results in a non-radiative process, non-radiative deactivation, and to explain this, Stern-Volmer equation is mainly used. Stern-Volmer constant, which KSV, which is defined for dynamic quenching, the Stern-Volmer constant is equal to the product of quenching constant and the tau naught, which is defined as the lifetime of the fluorescence, means the time duration for which the fluorescence light is emitted in absence of quencher. That time duration tau naught, when multiplied by KQ, the equilibrium constant, it gives us the value of KSV, the Stern-Volmer constant. In case of static quenching, as I told you, it involves a ground state complexation in which the quencher reacts with the fluorescent molecule or the fluorophore in the ground state and does not allow the molecule to go into excited state. Clear? And in this case, a modified Stern-Volmer equation is used. That modified Stern-Volmer equation is I naught upon I is equal to 1 plus Ks Q, where Ks is the static quenching equilibrium constant, where Ks is the static quenching equilibrium constant. Again, if we draw a plot in which we plot tau naught upon tau on y-axis while we put quencher concentration on x-axis, this is the ratio of lifetime of fluorescence in absence of quencher and presence of quencher. Means tau naught refers to the fluorescence lifetime in absence of quencher, tau represents the fluorescence lifetime in presence of a quencher. It comes as a straight line. But due to these dynamic and static quenching, we may have some deviations from this linear relation. Although we have a linear relation between quencher concentration and the intensity ratio, although we have a linear relation between quencher concentration and ratio of lifetimes of fluorescence in absence and presence of quencher, but sometimes, as I told you, we have some deviations from this linear relation. This is upward deviation, then we have a downward deviation. Clear? And one more thing, the slope of this graph, the slope which is obtained from tan theta, theta is the angle, or it is obtained from taking the ratio of, for example, this, if this is P, this is Q, then tan theta or the slope is equal to P upon Q, and this is called as Stern-Volmer constant. So if we plot a graph between tau naught by tau versus Q, quencher concentration, the slope of that graph gives us the Stern-Volmer constant value. In some cases, we have deviations from this linear relation. So the causes of non-linear deviations, so the causes of these non-linearity are in the Stern-Volmer plot. In the Stern-Volmer plot, these deviation occur due to quenching. Even for a purely static quenching, we observed a linear relationship between Stern-Volmer constant but because static quenching does not affect fluorescence lifetime, because it is a static quenching. Here the quenching is taking place in the ground state only. The molecule is not going to the excited state. But in case of dynamic quenching, it reduces the lifetime of the, because if dynamic quenching is not taking place, it exists for a longer period of time in excited state. But since dynamic quenching is taking place, the lifetime changes. So we can say that dynamic quenching changes the lifetime of excited state, while static quenching does not affect the lifetime of fluorescence. And therefore we observe two types of deviation. The upward deviation is because of the simultaneous presence of both static and dynamic quenching, although static quenching does not affect much, but dynamic quenching affect the linearity because it changes the lifetime. And then a downward deviation exists when we have two types of fluorophore, means two types of fluorescence emitters, and those emitters have different Stern-Volmer constant, and because it creates a complicated phenomena, as we have two fluorophores like fluorescence emitters and we have two different KSVs, that created a downward deviation. So we can say that although this graph from which we calculate the Stern-Volmer constant, this is linear. The Stern-Volmer relationship is linear, means the graph of tau naught by tau versus q, or since tau naught by tau is also equal to I naught by I, so we can say that tau naught by tau or I naught by I versus q gives a straight line, because and that from the slope we obtain KSV. But in some cases, when both static dynamic quenching is taking place, we have some deviations. Although if only static quenching is taking place, no deviation from this model, because static quenching does not affect the lifetime, means it does not affect the value of tau, because since the quenching takes place in the ground state, the molecule does not, the fluorophore does not reaches the excited state. While in case of dynamic quenching, since the fluorophore reaches to the excited state, if dynamic quenching is not taking place, it may have a longer lifetime, but if dynamic quenching is taking place quickly, it may have a shorter lifetime. So we can say that dynamic quenching affect the lifetime of fluorophore, and since it is affecting the lifetime, it is affecting the value of tau, we may have deviation, and two types of deviation: upward deviation and downward deviation. Now upward deviation occurs when we have both these quenching, static and dynamic quenching taking place together. We have this upward deviation. While in case of downward deviation, we actually have in a sample two fluorophores. We have two fluorescent molecules which causes the emission of light, and because of these two fluorophores, we have two Stern-Volmer constant here in this case, KSV1 and KSV2. Because of these two constants, we have a complicated phenomena, and therefore the relation between I naught by I versus q, or tau naught by tau versus q, does not remains linear, it goes non-linear, and we observed a downward deviation. So this is all about the Stern-Volmer constant. So this is all about Stern-Volmer equation as well as the Kasha rule and Vavilov's rule. Now we'll discuss few examples, or now we'll discuss about few problems relating to fluorescence spectrum. And one more thing, in many systems at low concentration of quencher, means if the value of Q is low, we have a linear relationship, but at high Q concentration we have non-linear. It may be upward or lower, downward, but for low quencher concentration, we have a linear relationship. Clear? So this is also an important point, that if the quencher concentration is low, we have a linear relationship, while we have a linear Stern-Volmer relationship. On the other hand, if the quencher concentration is high, the linear relationship gets converted into non-linear relationship, and we may have upward or downward deviation from Stern-Volmer relationship. Clear? So let us discuss few problems relating to fluorescence spectroscopy. The first problem, the first scenario: a chemist is using fluorescence spectroscopy to measure the concentration of a fluorescent dye. A standard solution of the dye with a concentration of 10 power minus 6 molar low concentration gives an emission intensity of 4.8 millivolts. An unknown sample of the same dye, means this is for calibration purposes, an unknown sample of the same dye produces a reading of 2.2 millivolt under the same instrument. What is the concentration of the unknown sample? Because the concentration at this concentration, the signal is 4.5. What is the concentration at 2.2 millivolts? The question is the concentration. So for this, we use the concept of calibration curve. From there we can have this relation, means because the fluorescence intensity with concentration, there is a direct relationship, they are linearly related. So we can say that fluorescence for sample upon fluorescence for standard is equal to concentration of the sample upon concentration of the standard. This formula has been applied. So 2.2 millivolts is the intensity, and earlier we have 4.8. while we need to know the concentration of sample, while it is 1 into 10 raised power minus 6. We do the calculation and we finally obtain that the concentration of the sample is 4.53 into 10 raised to the power minus 7 milli 4.53 into 10 raised to the power minus 7 moles, or it can also be written as 0.453 10 raised to the power minus 6 molar, while in case of the standard it is 1 into 10 raised to the power minus 6. So this is having less concentration as compared to the standard. Then another question, look at this scenario. A fluorescent molecule in solution has an initial fluorescence intensity of 8 millivolts. After adding a quenching agent, since we are adding a quenching agent, of course there should be a decrease in intensity. The intensity drops to 5.5 millimole. So we put this I naught is 8 millivolts, then I is 5.5 millivolts, 1 plus KSV, the concentration of Q is 0.6 molars. We divide it, we get 1.45. This is 1.45, 1 plus KSV 0.6 molar, then we subtract it, we get 0.45. This we solve it, and the value of KSV is 0.75 per mole. The value of Stern-Volmer constant comes out to be 0.75 mole inverse. Again, there is another scenario. You obtained the fluorescence excitation and emission spectra for a new compound. The excitation peak comes at 350 nanometers, while emission peaks comes at 410 nanometers. So the question is, what is the Stokes shifts in nanometers for this compound? As we all know that when we have spectrum like this is excitation, this is emission. The difference between these two maxima is the Stokes shift. We subtract these 410 minus 350, the answer is 60. Then the second question, why is the emission peak at a longer wavelength than excitation peak? We all know that due to relaxation, due to vibrational relaxations in the excited state as well as internal conversion, some energy is lost as a non-radiative energy, and the remaining amount of energy is emitted when electron comes back. So this energy is always lesser than the energy which is being absorbed, and therefore the emission occurs at longer wavelength. If you want to perform a quantitative measurement, what excitation would you choose and why? This we'll discuss. So again, the Stokes shifts, just by subtracting the excitation and emission wavelengths, we get 60 nanometer. And for the second question, why it is emitting light at longer wavelength? Because some of the energy is lost as non-radiative process, like vibrational relaxation and even due to internal conversion. So this causes energy of the molecule to go to a lesser value, and that lesser energy is released when it comes back to ground state in the form of visible light. Therefore less energy means longer wavelength, and therefore we observed at longer wavelength. So this relation, as I just mentioned, that due to internal conversion and vibrational relaxation, some energy is lost, the remaining energy is released. Of course, since the energy is low, it releases with longer wavelength. Now the third question is, what wavelength would you choose and why? The optimal excitation wavelength to choose is 350 nanometer, which is already given in this question. This is because the wavelength, as I said, according to Vavilow's rule, the excitation wavelength does not affect the wavelength of the emitted light. It only affects the intensity of the signal. So this is because the wavelength corresponds to excitation spectrum maximum. Exciting the molecule at this wavelength ensures the most efficient absorption, which in turn produces most intense fluorescent signal and the best sensitivity for the quantitative analysis. Therefore, we are not going to change the wavelength, as it is already given that this is the optimal excitation wavelength for this sample. Means it is the lambda max at which maximum absorption is occurring for this particular molecule. If we change the wavelength, lesser absorption will occur, and therefore the therefore the intensity of the emitted signal would be low. Although this wavelength does not affect the wavelength of the emitted light, means it is not going to change the x-axis value, but of course it changes the signal height, means the intensity of the fluorescent light. Therefore, if we choose some other wavelength, the absorption will not be very high, because this particular wavelength is the optimal wavelength already given in the question. which means it is the lambda max at which maximum absorption occur. When maximum absorption occur, the intensity of the emitted signal would also be high, and for high signal we means better sensitivity of the spectrum for this particular quantitative analysis. So we'll keep this excitation at this same value only. Now we have another question. If we record an excitation and emission is maxima for a fluorophore, means for a fluorescent sample at 330 nanometer and 465 nanometers. So there is a big difference, means at 330 it is absorbing light causing excitation and it is emitting light at 465 nanometers. What is the Stokes shift again, and then convert Stokes shift into wave number. First of all, we calculate the Stokes shifts just by subtracting 465 and 330. We'll get 150. 465 and 330 will get 135 nanometers. So this 135 nanometer is the Stokes shift. So 135 nanometer is the Stokes shift, means it is the difference in the wavelength maxima. Now in the second part, we have been asked to convert this into wave number, and as we all know that wavelength and wave numbers are reciprocals of each other, means lambda is equal to nu bar. Nu bar is the wave number, or if you want to calculate nu bar, it is equal to 1 upon lambda. So in this case it is 1 upon 135 nanometer, and we all know that 1 nanometer is equal to 10 raised to the power minus 9 meters, or it is 10 raised to the power minus 7 centimeters. So finally it will become 1 upon 135 into 10 raised to the power minus 7, which ultimately goes in numerator 10 raised to the power 7 upon 135, which turns out to be something around 8,000, which turns out to be something around 8,000, 8798, of course centimeter inverse. Its unit is centimeter inverse because we have put this conversion here. So we have two ways to do this calculation. First of all, either we can convert both these wavelengths into wave number and then take the difference, or we first of all take the difference. The answer is 135, and then we can convert this 135 into wave number. So I have explained you by noting down the difference in terms of wave length and then convert it into wave number. In this solution, we have given the other method, 335 nanometer, again 330 into 10 to the power minus 7, then it is being converted 3.3 10 to the power minus 5 centimeter, again 4.75, it is converted in terms of centimeter. This wavelength has been converted into centimeter first of all. Then because we are going to calculate wave number, which is reciprocal of a wavelength, so wave number is calculated by, for excitation, this wave number is 1 upon 3.3 10 to the power minus 5, comes out to be 3000, it comes out to be 30,303. Then for emission, again reciprocal of wavelength, 1 upon 4.65 10 raised to the power minus 5 centimeter, it comes out to be 21,000. When we take the difference is 8798. A little bit long process, therefore it is better first of all to just to subtract the two wavelengths to obtain the Stokes shift, which is 105 nanometer, then directly convert it by this relation. 10 power 7 upon 105 will give you the value of wave number, which is 8798. This is the easiest way of solving this question. Another question, a fluorescence peak comes at 500 nanometers. Fluorescence peak means it is the emission peak. Now what is the wave number in centimeter inverse? As I just told you, if you want to convert wavelength into wave number, just do the reciprocal, and since it is in nanometer, answer is required in centimeter. Just put 10 to the power 7 in numerator, while the value of wavelength in nanometer here. Do the calculations. It turns out to be 10 raised to the power 3 into 10 raised to the power 4, just for solving our question. This 10 raised to the power 3 becomes 1000, upon 500 we have. This is 10 raised to the power 4. This turns out to be 2. Then we have 2 into 10 raised to the power 4 centimeter inverse is the answer. 2 into 10 to the power 4 centimeter inverse means 20,000 centimeter inverse is the wave number corresponding to this wavelength of 500 nanometers. The last question, light with wave number 25,000, speed of light we all know around 3 lakhs. We consider in kilometers per second, but it is exactly equal to 2.998 10 raised to the power 8 meter per second, or it is 2.998 into 10 raised to the power 5 kilometers per second, although it is given in centimeters. So from meter we convert it into centimeter. Again we multiply by 10 raised power 2, so it becomes 10 raised power 10 centimeters per second. Now wave number is given, speed is given. We have been asked to calculate the frequency, and we all know that V is equal to n lambda, and we all know that V is equal to, and we all know that C, which is the speed of light, it is equal to frequency into lambda, the wavelength. And since lambda is equal to 1 upon nu bar, wave number, because they are reciprocal, we convert this equation into the form of wave number. So this is speed of light, then we have frequency, and then lambda is replaced with nu bar. We do cross multiply, the wave number comes here, and equation becomes nu upon C. Now frequency is being asked. Frequency will be equal to C into wave number. So it is 2. So it is 2.998 10 raised to the power 10 multiplied by 25,000 means 25 into 10 raised to the power 3. It will become 7.495 into 10 raised to the power 14. It will become 74.95 into 10 raised to the power 13, or frequency will be 7.495 into 10 raised to the power 14. This is the answer in per second. Or we can also do it like that we first convert this 25,000 into wavelength. This 25,000 can be calculated into wavelength by 1 upon 25,000. So it will become 4 into 10 raised to the power minus 4. It will become 4 into 10 raised to the power minus 5. The wavelength means it is 400 nanometers. So we put this value because it is in centimeter. Here velocity is equal to frequency into lambda. Velocity is equal to frequency into lambda, and frequency is equal to velocity upon lambda. So in that way this frequency will be equal to 2.998 10 raised to the power 10 divided by 4 into 10 raised to the power minus 5. Again it turns out to be 7.495 into 10 raised to the power 14 second inverse. So we can calculate it the either way, either by first of all changing nu bar wave number into wavelength and then applying the formula C is equal to frequency into wavelength, or we directly apply the formula C is equal to frequency into wavelength and then convert wavelength into 1 upon wave number, and then by the relation of frequency is equal to speed C into wave number we multiply and get the answer. So in this way we can calculate the value of frequency, and this is how we perform and this is how we solve problems relating to fluorescence spectrum. With this, I hope I have covered all the aspects of And so with this I hope I have covered all the aspects of molecular luminescence spectroscopy, including the photoluminescence, fluorescence, phosphorescence, including the photoluminescence as well as chemiluminescence. In photoluminescence, I have covered fluorescence, phosphorescence, the instrumentation of fluorescence, the principal methods of taking fluorescence measurement, like and methods of methods of measuring the fluorescence intensity of a sample by direct method for naturally fluorescent compound, and indirect method of derivatization or quenching methods for non-fluorescent compounds. Then we have studied about few rules like the Kasha rule, Stern-Volmer equation, as well as the Vavilow's rule, and finally we have solved few questions. So with this, I hope that you have learned about these molecular luminescence spectroscopy, and now you will be able to solve questions related to this particular topic. With this, I am again very thankful to all of you for patience viewing this. With this, I am again thankful to all of you for patiently watching my lectures, and I hope these lectures would help you to improve your understanding about the topics of advanced analytical techniques, and you will get success in your career. Take care. Thank you very much.